Just click go live. Yeah, Prahlad, you can start.
Okay. Let's get started. So the main agenda today is to introduce NP completeness, polynomial time reductions, and the Cook-Levin theorem. So last time we had defined the class NP, and we saw examples of problems in NP. We saw things like SAT, independent set, composite, the traveling salesperson problem, etc. We saw several of these. And what we will see, so in fact, some of you did comment that not all of these problems are actually hard. For example, we do know how to solve composite now in polynomial time. So we'd like to understand what is the comparative hardness of these problems. So for that, we'll recall the notion of reductions that some of you are possibly familiar with from the theory of computation. In particular, we'll define a notion called polynomial time CARP reductions, or just polynomial time reductions. So let L1, L2 be two languages. Say that L1 is polynomial time reducible L2. L1 is polytime reducible to L2 if the following condition is met. If there exists a polytime computable function F that maps strings to strings such that X is in L1 if and only if f of X is in L2. So let's just look at this. So let's look at one world in which you have, this is 0, 1 star. This is L1. L1 is this subset of strings. And then you have another 0, 1 star. And you have L2 over here. And F is a map from 0, 1 star to 0, 1 star. So it's a map from this world, it's a map from here to here. But F has the property that takes things in L1, it takes into L2. Things outside L1, it takes outside L2. So it maintains the membership of it. The L1 has this feature. The F has this feature. And by the way, what do I mean by F? What do I mean by F? That is, there exists a deterministic Turing machine M and a polynomial P such that f of X is computed by M and M runs in time at most P mod X on input X. So this is what we would mean. This is what I mean by saying L1 is polynomial time reducible. Particularly, it takes things inside to take things inside, takes things outside. Outside. Notice that this is a usually what do we want to capture by the notion of reduction? I want to say that if I can solve L2, I can solve L1. This is the thing I want to say. That is, if you give me an algorithm that solves L2, I want to solve L1. These are what are in general called subroutine reductions or Turing reductions. This is a more specific type of reduction, CARP reduction, in which I want to capture the fact that if L2, you're able to solve L2, you can solve L1, but in a very specific fashion. That is, how do you solve L1 given L2? You want to solve a particular problem L1, you You start off with an instance for x. You first do this computable function f. You compute. Now, instead of an instance of L1, you now have an instance of L2. You just apply f, you get an instance of L2. And now once you have an instance of L2, you run the algorithm for L2 and you output whatever that algorithm tells you. You don't try to massage their output in any particular fashion. You have an algorithm for L2, you just output whatever that algorithm tells you for L2. If it says, yeah, that particular f of x is in the language L2, you output the same thing. So whereas in subroutine time reductions, you could take the answer for L2, massage the answer, and then to find out what the answer for L1 is. Here, no, because of carp reduction, it's a very specific reduction. You first run the reduction f, which maps this way. So suppose I give you, intuitively, suppose I give you an algorithm. So suppose I give you an algorithm for P. What is the algorithm for L1? Given by, say, Turing machine, say n. So the algorithm for L1, say that n prime, is the following algorithm. On input x, compute f of x, run n on f of x, and output the answer. Okay, so this is the notion of reduction, and given that, and furthermore, this reduction has to run, this computation, this part has to run in poly time. So specifically, I want this computation f should happen in polynomial time, and that's important. Later on, we will see refinements of this in which we will say it's not just polynomial time, we will make it even more restricted. For now, we'll work with polynomial time, and this P over here refers to this polynomial time. The P over here refers to the polynomial time. So when I want to say polynomial time reducible, I'll put a less than or equal to with the P below, which refers to polynomial time reducible.
Prahlad, whenever you write a Turing machine n, these are all, they could be non-deterministic, right?
No. If I don't say anything, they will always be deterministic Turing machines.
Okay.
If I'm going to use anything, I will specifically say it's a non-deterministic Turing machine or a randomized Turing machine. I will make that point clear. So if I don't mention anything, it's always deterministic Turing machines. Okay. And now last time I wanted to also so this notion of reduction tells you, by the way, so in particular, if I have a reduction from L1 to L2, that means L2 is at least as hard as L1, because once I solve L2, I can solve L1. That's what this one tells you. So in particular, we can ask, you can use this notion of reduction to capture what is the hardest problem for a class. So in particular, we can define the notion of NP hard. We'll say that L is NP hard if for all languages L prime in NP, L prime is polynomial time reducible to L. Therefore, everything in NP reduces to this particular problem. So L is the sort of the candidate hardest problem, is sort of as hard as any other problem in NP. If furthermore, if we know that, say, L prime was in NP and L is NP hard, then I'll call L to be NP complete. So L is not only as hard as any other problem in NP, it is also in NP. So it's sort of the candidate hardest problem in NP. It captures the hardness of every other problem in NP. Of course, this is a nice definition. We need to show that there is some problem which is NP complete. If there's no problem which is NP complete, it's a vacuous definition. There's no point in it. So the main focus of today's lecture is actually going to see there is a plethora of problems which are NP complete. And the starting point for this will be the sort of. So let's I want to say showing that a problem is NP complete is not really very hard. We can easily come up with a problem. So let's look at an example of an NP complete problem. Any questions so far? An example of an NP complete problem is what I will call Turing machine satisfiability. What is the instances of this problem? The instance, it's a 4 tuple. The first is a description of a Turing machine. Next is an input X. It's a description of a non-deterministic Turing machine. An input length n and an input length n bound and a time bound t bound. And it just says the following: alpha is a non-deterministic Turing machine, and there exists a string u of length n such that m alpha accepts the pair xu in 1, accepts the pair in time t steps. Is the definition of this problem clear? So it's just, I'm specifying, it's the inputs, the instances, input instances are of 4 tuples. It's a description of a Turing machine, an input, a bound on the witness length, and a bound on the number of time steps. And I want to claim this is trivially an NP complete problem. So how would you show? So I want to claim that I want to make a, it's not even worth a claim, it's just an observation. That if L belongs to NP, implies L is polynomial time reducible to TM set. So what's the, so if you want to show this, you have to display to me what's the function f, the polynomial time. So what is the function f? So how would you do this? Let's, to help you, let me say, so L is an NP. In particular, that means there exists a Turing machine M, a deterministic Turing machine to clarify, and polynomials P and Q such that X belongs to L if and only if there exists a U in, I'm just recalling the definition of NP, the witness definition, such that MXU equals 1 and M runs in time Q mod X. So I give you this. So now I want the function f, the polynomial time. So what is it going to map? You have to give it, X should get mapped to something. So what is the 4 tuple you will map it to?
The string corresponding to m.
Yeah, so that's, just say this thing corresponding to m. That's constant length. It's a fixed, it doesn't depend on the input length at all. Yes?
N is p mod x and t is q mod x.
So x, you give 1 to the power p mod x, and 1 to the power q mod x. And this, you should now notice that this, whatever I have written over here, and whatever is written over here exactly match. So X will be in the language L if and only if this is in the language TM-SAT. That should be clear from the way I stated it. So TM-SAT is a candidate NP. And furthermore, is TM-SAT, so TM-SAT is NP hard. Is TM-SAT also an NP?
Yes.
Why is that an NP?
Because of the universal Turing machine. It will accept, I mean, it can simulate any Turing machine.
Is it Matthews?
Yeah.
Yeah, okay.
Like
Yeah, because of the existence of the universal Turing machine. And the universal Turing machine can simulate something. If something simulates it in t steps, it takes hardly any more overhead. It will take just a logarithmic extra overhead. We saw t square overhead. That's why you can do this. Okay, so that's good. So we do know that the conclusion of all this is the fact that TM-SAT is NP hard and TM-SAT is an NP. These both are, actually trivial observations, which means TM sat is NP complete. And this sort of NP complete problem is very typical to the sort of complete problems we did when we studied theory of computation, the halting problem and these problems. So given a particular class, you can very naturally come up with a syntactic class. I won't define what syntax is. For these classes, you can come up with a very natural notion of complete problem, which is this one. But these, I want to claim, these somehow don't capture the richness of the class. We will actually show that we'll prove actually in the rest of the lecture, we'll prove a different problem is NP complete. And somehow that helps us to capture NP in a much nicer sense. This one, of course, TM sat does capture NP. It's NP hard, it's NP complete. So it does capture the definition of NP, but that's all it does. It's just a rewriting of the definition of NP. So what we will see is the famous Cook-Levin theorem, which was proven independently by Cook and Levin on two different sides of the Iron Curtain, in which they showed that SAT is NP complete. And in particular, they also showed that a very specific case of SAT, which is 3-SAT, is also NP complete. That's going to be actually the highlight of today's lecture. We will do the Cook-Levin. We will see what the consequences of the Cook-Levin theorem and prove the Cook-Levin theorem in lecture today. Okay. Any questions so far? So what is SAT again? Let's just quickly recall what is SAT. SAT is, so phi is a Boolean formula. And we'll assume it's written in conjunctive normal format, in a CNF format. That is basically phi is written in the form of C1 and C2 and Cm, where each Ci is a clause. What do I mean by that? That is, it is a disjunction of literals. That is, it's of the form, each Ci is of the form Li1 or Li2 or Li, sorry, should I call it Lj1, Lj2, Lj, Lj, where each Lk itself is either X or X bar. So, and SAT is set of all phi. Phi is a CNF formula that is satisfied. So I'll spend some time in a couple of minutes why actually CNF formulas are nice, why we'll work with one. And a special case of this is 3-SAT. So we'll work with 3CNF. I'll say phi is
CI need not have I literals, right? Or
what?
the CI need not have I literals, right?
That's right. That's right. So let's put some JMI.
Yeah.
Some fun. Phi is 3CNF if each clause has at most 3 literals. That's less than or equal to 3 literals. And 3-SAT is a subset of SAT when you restrict to 3CNF form. Okay. Somehow we will show that knowing that SAT is NP complete and 3-SAT is NP complete, this fact conveys a little more about NP than just the fact that TM SAT is NP complete. We showed that TM SAT is NP complete, SAT is complete. And the reason is the richness with SAT. SAT is some problem which sort of doesn't refer to Turing machines at all. It's a conjunction of clauses, and so just a conjunction of clauses. And we'll use this fact to show that not only this theorem, Cook-Levin theorem, not only can you show SAT is NP-complete and 3-SAT is NP-complete, it actually will show you that several other problems are also NP-complete. That's the richness of this. And so before let's defer the proof of Cook-Levin theorem to more see how Cook-Levin theorem can be used to proving several other classes, other problems are also NP-complete. We'll do that first and then get on to the Cook-Levin theorem, proof of the Cook-Levin theorem. So a couple of quick properties of reductions that I will need. Properties of polynomial time reductions. Let's. The first one I want to say, suppose L1 polynomial time reduces to L2 and L2 polynomial time reduces to L3. What can you say about L1 and L3?
L1 reduces to L3.
Huh?
L1 reduces to L3.
So L1 polynomial time reduces. And why is that true?
So you can first take the input of X, like input of L1 and send it to L2 and then again apply the polynomial reduction for L2 to L3 and then solve.
Okay, fair enough. You do. Why is that? Why is that a polynomial time reduction?
Because the polynomial of a polynomial is a polynomial.
Yeah, so you use the fact, this robustness of polynomials is quite, I think you mentioned it in the first lecture itself. A polynomial of a polynomial is another polynomial. That's nice about the fact. That's why, so you have this transitive nature because of this. I'm not writing the proof of it, but hopefully it's evident. That is, this you're running the first reduction, taking the output of it, running the second reduction. So the total time taken is the time taken by the first reduction and the time taken by the second reduction. But notice the second reduction, its input is not the input of the first length. It's already a polynomially long input. So the second reduction is a polynomial of a polynomial, which is still a polynomial. Okay, so that's the first thing. We'll use the transitive nature of polynomial time reductions. By the way, notice that this transitive nature is not, you can't do it, you can do it a constant number of times. You can't do it more than a constant number of times. I can't say L1 polynomial time reduces to L2, L2 polynomial time reduces to L3, L3 reduces to polynomial time. As long as that's a constant, a polynomial of a polynomial of a polynomial, a constant number of times is a polynomial. But the moment you go to a super constant number of times, this is no longer true. So transitivity is, you don't have like complete freedom in transitivity. You just can't write a chain of things and then say it's a polynomial time reduction. You need to know that the chain in this thing is a constant chain. Okay. That's the first thing I want to say. The next thing I want to talk about these reductions is something which we already observed. I'm just writing it down. Suppose you prove L is NP hard and then manage to show L is in P. What does that imply?
P is NP.
Yeah, so NP will collapse to P because of this, or NP equals P. The main important direction is NP collapses to P. Finally, suppose L is NP complete. We have a similar reduction. So, in other words, the step 2 states that if you want to prove NP is in P, the thing to show is just take some NP hard language and show that it is in P. If you show that, you'll show the entire class. So, even if one single NP hard problem falls in P, it brings with it the entire class NP into P. That's what the item 2 states. Item 3 is going to be a refinement of this. What it's going to say is, now L is in P. Of course, we already saw this implies NP is in P. But I want to say, so this direction we already saw. If L is NP hard itself, but I want to say the other direction is also true. If NP is in P, then L is certainly in P, because this is because L is NP complete. Therefore, the third statement shows that in order to show NP is in P, second statement to show that NP is in P, it suffices to show that some NP hard problem is in P. The third one says, in order to show NP in P, it's not just suffices, it is necessary for us to show that an NP complete problem is in P. This is the only way. If you want to show NP is in P, you have to show every NP complete problem, or even one NP complete problem is in P. This is, you can't escape showing that. This is what you need to show. It's both it just shares a necessary and sufficient condition. instructions, and we'll keep this in. So okay, now let's go back to, so we saw the 3-sat. We use the start the point, the 3-sat is NP complete. So I want to know as a first example of what are other NP complete problems. No, now notice, now once you know 3-sat is NP complete, to show that some other problem is NP complete, what do we need to show? We only need to show that 3-sat reduces to that other problem. Once we show that, the other problem also, every other problem in NP will reduce to 3-sat, because this is because of transitivity. Because the definition of 3-sat being NP complete says every problem in NP reduces to it. And then if you reduce 3-sat to that other problem, that suffices to show that other problem is NP complete. So what are other NP complete problems? So I'm going to, let's start off with one example. I'll do 2 examples in this lecture, and then your first problem set has tons of problems for which you have to show whether they are in NP, NP complete and stuff. So let's start off with example 1, which is integer linear programming. In fact, let me make it even more simple. Let's make it, even among integers, let's make it 0, 1 linear programming. So the instance over here is a bunch of linear inequalities. Say x1 plus x3 plus x5 is greater than or equal to 10, x1 minus x2 is greater than or equal to 8. It's some m such inequalities. And finally, the fact that all the xi's have to be 0, 1. They are not any arbitrary real numbers. They have to be real. They have to exactly 0, 1 real numbers. So I give you a bunch of inequalities, and the question is, the problem is, are they satisfiable? Is there a setting to the variables that makes all the linear inequalities true? That's the problem. So in particular, 0, 1 IP. So let's just let me just, for shorthand, I'm going to say IP is this instance psi. Psi is a satisfiable 0, 1 integer programming instance. I want to now say that 3-sat reduces in polynomial time to IP. Why is that? And people see reduction. So basically, I give you a phi. You need to give me a polynomial time reduction that maps it to a psi, an instance of this form. How would you do it?
For every clause in phi, you can make an inequality.
Yeah. So let's take a clause. So suppose we have the clause x or y or z complement. So what would be a
yeah.
Let's. So what will be the inequality I'll put here?
X plus y plus 1 minus z.
So x plus y plus 1 minus z is
greater than or equal to 1.
Greater than or equal to 1. So we can just convert. This is a more natural format. Every positive literal you retain as it. Every negative literal you replace it by 1 minus x and say the sum of these things should be greater than or equal to 1. Now note, and then we'll further add the conditions that x, y, z, these all have to be 0, 1. Notice that the only solution to this will have to be a satisfiable assignment. So if this target integer programming instance is satisfiable, the only way it is satisfiable is the original 3-sat instance were satisfiable. So IP is also, and it's easy to see it's NP complete. It's easy to see it's an NP because you give me a 0. If there is a 0, 1 solution, you can give it as witness, and you can easily check that is a satisfiable instance. So IP is NP complete. Is NP hard? The above says IP is also in NP. This is a bad acronym IP, but we'll see that why it's a bad acronym 10 lectures from now. So IP is NP complete. Okay. Yeah, so this is a simple example to illustrate the power of 3SAT. 3SAT being such a simple problem which is NP complete. Now you manage to show now IP is NP complete. We'll now look at example 2, which is the independent set. Problem. And the decision version of this is what is usually called ind set, which is you're given a graph and a number k, and says that there exists an independent set.
Last, can we say that IP is polynomially reducible to 3SAT?
That is true just because IP is in NP, and because 3SAT is NP hard, every problem in NP reduces to 3SAT. That's the Cook-Levin theorem. We haven't yet proved it, but that's the Cook-Levin theorem is telling you that. This theorem.
So, if these constants are not one, other than one?
Other than, so by the way, this reduction only goes in one direction. This reduction doesn't go in the other direction. The reduction only maps 3SAT to IP. If you want to show IP maps to 3SAT, you have to do a different reduction.
Okay.
So your question is a valid question. So the question is, how do I do the reduction going the other direction? And I claim to you, I will not just show it for IP. We will eventually, by the end of this lecture, show it for every single problem in NP. I will give you a reduction from that problem to 3SAT. So it could be, the thing could be integers and stuff, but yet the reduction will run, and I'll give you a polynomial time reduction. Just defer the question till the end of the class, and by then you should see it. So I won't give a tailor-made reduction for IP to NP. I'll just take the general property that IP is in NP, and from that, Cook-Levin theorem will conclude that IP reduces to 3SAT. By the way, it's important. Your question is this one. Here, the confusion is the reduction is going from 3SAT to IP. It is not going from IP to 3SAT. And that's important to notice. These reductions are one way. It so happens there exists another reduction going from IP to 3SAT. And that we know it. You can either come up with a tailor-made reduction for this particular problem, or you can just resort to the Cook-Levin theorem and see that there is a reduction on that side. The undirected graph. So clearly ind set is an NP. That's something which we know.
This means is like
Pardon?
what this means is like the set of vertices where there is no edge between any of these.
So an independent set is basically a set of vertices such that there's no edge between any of those two vertices in that set. There could be edges going out from that set to the vertices outside this set, but within this set they are independent. There's no connection between any two vertices in this set.
Okay. Yeah.
And it's clearly a problem in NP because suppose there were an independent set of this size, you could give that as witness, and now you just need to check that there is no edge between them. What we now want to show, I want to make the lemma which I want to now prove is 3SAT polynomial time reduces to ind set. Okay. This is actually a very clever reduction. It's a reduction due to Karp. And there's a reduction which actually come to again and again a couple of times later on. So what do we want to do in the reduction? So we want to come up with this function f that, given a formula, maps it to a graph and a number, such that you have the following feature. phi is in 3sat if and only if g phi, if and only if g phi k phi is an independent set, but let me write it a little more. There exists an independent set of size k phi in g phi. This is what we want to put. This is the reduction we want to construct. We'll actually do it in a very nice fashion. This is, so suppose phi is this. Phi is a, we'll use the fact it's a 3-sat formula. Phi is a conjunction of clauses. It's m clauses, and say the ith clause looks like something of the form xi1 or xi2 or xi3, something like that. It looks like this. We are now going to use this clause to construct a graph. So let me first describe what the graph is, g phi. So I will describe both its vertices and its edges. So the vertices, are going to be, so let's first describe the vertices of this graph. I'll first give this one and first give sort of a formal description and then actually give you this one. It's sort of going to be, actually let's say, it's going to be split into m clouds. There will be m, the vertices will have m clouds. Each cloud will stand corresponding, the vertition will be partitioned into m parts, or clouds are part. There'll be, the vertices will come in m parts. Each part will correspond to a clause in some sense. Each part will correspond to a clause. And what will how many vertices will be in each cloud? Each cloud is going to have 7 vertices. So actually, so V phi is going, we are going to come up with V phi, which is just 7, size of them is going to be 7 times m. Each cloud is going to have 7 vertices. And what are the, so the vertex, there will be what are the 7 vertices? So once you have a cloud, so this will correspond to the clause C1. This will correspond to the clause C2, C3, and say Cm. So the cloud corresponding to the clause Ci, the 7 vertices here will refer to the 7 satisfying assignments in clause Ci. So clause Ci has just 3 variables in it. 3 variables. So to satisfy it, you only need to set these 3 variables in a particular fashion. And because it is a clause, so there are 3 variables, therefore there are 8 possible assignments, satisfying assignments. There's 8 possible assignments, but exactly one of them is a violating assignment. The remaining 7 are all satisfying assignments. So what I'm going to put here is I'm going to put all those 7 which are satisfying, and I'll take off the one which is the violating assignment. That's going to be the graph. The vertices of this graph are going to be, take every clause, put for every clause the satisfying assignments, the 7 satisfying assignments corresponding to the class. Some clauses might have lesser than 3 variables, in which case if it's 2 variables, you put the 3, then it's a clause with just 2 literals, put the 3 satisfying assignments out there, a vertex corresponding to each one of them. Okay, and if it's a clause with just 1 literal, put the 1 unique satisfying assignment out there. Is that clear? Those are the vertices of the graph. What are the edges? E phi. So in some sense, I can describe the vertex. So the vertex, one way of describing V phi is the disjoint union over all I in M of the satisfying assignments to variables of Ci. That's V phi. So it looks like this. It looks like I comma k. I is the clause number, the clause index, and A is an assignment from where Ci to to 0, 1. But it represents that there are just 7 of them over there, where Ci and is satisfying, and is satisfying for. Okay. Now we need to describe what is edge. What are the edges of this? So I'm going to tell you when is IA connected to JB. So these are 2 candidate vertices. It could be a vertex over here. It could be a vertex over here and a vertex over here. I need to tell you if there's an edge between them. It could be 2 vertices in the same cloud also. So we'll put an edge. IA is connected if. So this is the definition of the vertex. So what is this definition I'm going to use? If IA and JB refer to inconsistent assignments. What do I mean by inconsistent assignments? So A is referring to some variables, B is referring to some other variables. If they have a common variable and in that common variable they are going to set it differently, then I will put an edge. If there are no common variables, they are not inconsistent because there's nothing to compare them. So you look at the variables that participate in the first vertex, look at the variables that participate in the second vertex. Each of the vertices is giving an assignment to them. If these 2 assignments are inconsistent on the intersection of the variables, then you put an edge. Otherwise, you don't put an edge. Is that clear? So let's go back to this. So that's the definition of this. So let's look at this graph again. So can you tell me within each cloud, what will be the edge structure?
No edges.
No edges?
There will be edges. If I
Click.
Yeah, sorry.
one,
Click.
Yeah, well, okay, either way. So no edges, why? Click, why?
Yeah, it will be a click because there will be between any 2 functions, there will be a point of difference.
Yeah, so firstly, any 2 within a cloud refer to the same set of 3 variables, 3 or fewer variables, and they are all different assignments. They are 7 different assignments. So certainly on some variable, these 2 are disagreeing. So within each thing, actually, it will be a clique. So it will actually be you will have a clique over here, sort of. Within each cloud, it will be a clique. Across clouds, if they are talking about the same vertex and they are inconsistent, they will be an edge. Otherwise, they won't be an edge. Okay. So just an observation. What we just said, each cloud.
So by clique, you mean that every vertex is connected, right, with the other?
Yeah, it's a complete.
graph.
Each clique is a K7 over there. Okay. So this graph looks like there are copies of K7s. There's a K7 here, a K7 here, a K7 here, a K7 here, and then there are further more edges going across. Okay.
Yeah.
And now I'm going to define K phi to be equal to M. Notice M is the number of clauses. What do I need to show? I need to show that if phi is satisfied, this is the reduction from G phi to K phi. Now let's look at it. If phi is satisfiable, I want to say that there exists an independent set of size greater than or equal to M in G phi. Why is that true? In fact, I want to say this is an if and only if. So let's look at both directions. Let's look at the first direction. Why is this true? Suppose I have a satisfying assignment. What is the independent set that you would pick?
Take the assignments for each of the clauses, the vertices in each of these clouds.
Yeah, so you have an assignment that satisfies all the clauses. Look at the restriction of that assignment to each of these clouds. It's somewhere that that assignment is satisfying. Therefore, there is one one of them which corresponds to it. Similarly, here there's one, here there's one, here there's one. And notice that there cannot be an edge between any of them because these are consistent. They are not inconsistent. They are, whenever they share a variable, they are setting the variable to the same guy because they are all coming from one big global assignment. These are sort of like local assignments to the variables. What we have is a global satisfying assignment, and it sort of strings together. So if there is a satisfying assignment, there will be an independent set that picks one vertex from every cloud like that. And there will be no edges across that independent set. Now, conversely, suppose there is such an independent set. Suppose I tell you there's an independent set. What will be the, can you say that the 3-sat instance is satisfiable?
Yes, the independent set gives you a satisfier.
So the independent set gives you local assignments to each of the variables. It gives you the it tells you these 3 variables how to satisfy it. These 3 variables, these 3 variables, these 3 variables. But you need to know that all of these local assignments can be glued together to get a single global assignment. That is, they can't, there's no inconsistency. That this one doesn't say x1 is 1 and this one doesn't say x1 is 0.
But if that was the case,
there would have been an edge. There is no edge because you know it's an independent set. Therefore, all these local assignments are consistent. Therefore, you can glue them together to get a global assignment. And the global assignment satisfies every single clause because those are the vertices correspond to satisfying assignment. Therefore, this thing goes in either direction. This just basically proves this one, and that's the thing. So phi is in SAT if and only if there's an independent set of size at least m, which is k phi. People with me on this? Not writing down all the steps, but is it clear what this proof does? Notice this reduction is an extremely simple reduction. It's a linear time reduction. From 3-sat to vertex cover, you look at the 3-sat instance, just looking at the clauses, you can write down all the vertices. Then you can just go in another pass, write down all the edges of this one. That's all it needs to do. And it's a very simple reduction. It's a linear time reduction, but it has this nice property that if 3-sat is satisfiable, if and only if the corresponding independent set instance, the phi is a satisfiable instance of 3-sat, if and only if the corresponding instance g phi, k phi is in independent set, is an int set. Okay. So this an immediate corollary of this is the fact that int set is NP complete. Okay. And these two examples, both integer programming and int set, are primarily demonstrate that it's the simplicity of the SAT, fact that it is a clause, it has just three variables per clause, it's a 3-sat, that's what is actually lending itself to doing these reductions to these other problems. In fact, there's a web of reductions that you can come up with. It's possibly the notion of NP completeness is the most important export of theoretical computer science to the entire scientific community. And there are tons and tons by now. If you do a Google search for NP completeness, I think there are a few million problems that we know which are NP complete problems, which all are starting from reductions from NP from 3-sat or some other problem. And you'll already see a good half a dozen of these in your first problem set. Okay, so hopefully that tells you why the Cook-Levin theorem is a useful theorem to have. In the next half an hour or so, what we will do is we will see a proof of the Cook-Levin theorem. Any questions? Let's go to the next. Yes, proof of the Cook-Levin theorem. So even before I go into the proof of the Cook-Levin theorem, I want to say there's something nice about CNF formula. Why do I care that this is the niceness of CNF? We'll say that there is some universality about them, and this is what we will use while eventually proving Cook-Levin. There's a universality of CNF formula. Notice CNF, not all formulae are CNF formulae. Formula could have all sorts of this one, but I want to say the CNF form. So suppose you're given some function f on L variables. This is just a simple observation. I want to say that give me any function, then there exists a CNF formula phi of f such that phi f of a is equal to f of a for all a in 0, 1, 2, 3. So in particular, any formula that you want to write, you can actually write it as a CNF formula. And furthermore, the phi f has at most 2 to the L clauses of with L literals each. Write this in compact, stating that phi of f, the size of phi of f, is less than L times 2 power L. So now that with the furthermore, it should be evident. How would you? Why is this true? I want to say, give me any function on L variables, any Boolean function on L variables. I can write it down as a CNF formula, not necessarily 3 CNF, because it has L literals each. So it's an LCNF. Why is this true?
Brute force.
Sorry, I didn't catch. Who was?
Is it basically brute force?
It's just brute force. Take every possible. So what is a clause? A clause captures us. So take. There are how many assignments are there? There are totally 2 to the L assignments. Some of which are satisfied. Some of which cause the formula to f to evaluate to 1. Some of which cause f to evaluate to 0. So go over each one of these. So let's construct. So the furthermore should basically tell you what the proof is. So let's go over each of these assignments. The 2 to the L possibilities. So check if it is a satisfying assignment. If it sets the formula to 1 or 0. Say if it's set the formula to 0, you pick up that clause, that unique clause, which is violated exactly when it is this particular assignment. So you have particular choice. The clauses have this feature. It's an OR of several variables. If you exactly use the negation, you will choose that clause is violated exactly when it is this particular. So for every zero of the function f, you add a clause. That's it. This possibly is called the max term. Take all the possible max. I'm not sure for terminology. Possibly take all the max terms of the function f, and those are your clauses. Put them together. They are at most 2 to the L clauses. Each clause has L literals, and that's the CNF formula. People with me? I'm not writing down details, but do you follow me? If you don't, please do ask. I will.
So the ones that are mapped to 0, say x1 equal to 1, x2 equal to 0, this gets like xn equal to 0, this gets mapped to 0. For that, I have a clause which is x1 bar, whichever place 1 is appearing, I'm having a x1.
Yeah, so suppose
0, I'm negating it, and then I'm
f of x1 equals 1, x2 equals 0 happens to be 0. Then I will put the clause x1
or x2 bar
or x2.
Yeah.
Because this clause, when is it 0? This is 0 exactly when x1 is 1 and x2 is 0. So that will make the clause unsatisfied. So for every such L assignment that is a violating assignment, or one causes the f to go to 0, you put in a clause. Therefore, there are at most 2 to the L clauses. Each clause has at most each clause has L literals exactly. So we will use this feature of CNF formula. That's one thing we'll use. The other thing we'll use is the following thing. That is CNF formula. For example, I have two x and y, say, are both L-bit strings. L-bit strings. I want to write the fact that x is the same L-bit string as y. I want to say this can also be written as By the way, already this should be follow from what we have, but there's a much simpler formula which is just this. This is the CNF formula which says x1 or y1 complement and x1 complement or y1. Similarly for the ith. So I have this for it. So it's basically, I want to claim there is a 2L, there's a 2L clause formula that captures equality. Okay.
What's going on here? I couldn't.
No. What is this saying? By the way, the easiest way to see this is whenever you have x or not y, this is short for actually y1 implies x1. Think of it that way. It's short for y1 implies x1. So basically says if y1 is 1, x1 should be 1. And this is stating the other way around, x1 or y1. So it says x1 is 1, y1 is 1. If x1 is 1, so if you put these two together, this has to mean that x1 and y1 have to be the same guy. So you basically put these for every possible index. That's the thing. Okay. Now let's go into Cook-Levin. So we want to now show that let L be any n problem in NP. We want to polynomial time reduce L to SAT. First we'll do SAT, then we'll do 3-SAT. Okay. So to know this, firstly I need to recall what does it mean L is in NP. So L is in NP, that is there exists a Turing machine M and polynomials PQ such that X is in L if and only if there exists a U in 0, 1 e to the mod X MXU equals 1 and M runs in time Q mod X on input X. Now we want a polynomial time reduction. That means that we need to map X to a formula phi X such that X is in L if and only if phi X isn't satisfied. Okay. I want to say there's already a variant. So let's look at the formula phi X of U to be the formula. Let's construct the function phi X of U to be this function. Phi X of U. So phi X is some function. So given any X, I'm going to. So given an X, we need to construct phi X. But let's look at this function psi X. Psi X is the function going from 0, 1 p mod X to 0, 1, defined as follows. It takes any U to MXU. Clearly, X is in L if and only if psi X is satisfiable. That's almost said. So one thing we could do is just take the CNF curve, and I know psi X is some function. Our observation over here said that any function you can write it down as a CNF formula. So you can write the CNF corresponding to psi X because of the universality of CNF formula. So psi X has a CNF representation. Say phi of psi X. And that's clear that this phi is satisfiable if and only if psi X is satisfiable, and psi X is satisfiable if and only if X is in L. So we got the thing. Are we done?
But C is exponential in length, right? I mean phi. phi of psi x.
Yeah.
I mean, to construct that, I have to, your requirement is to reduce it polynomial. To construct that.
Yeah. So, very good. So it does show you a reduction, but it's not a polynomial time reduction. It is a reduction, indeed. This is a reduction. So the issue over here is, reduction doesn't run in time, does not run in polynomial time. Since phi of psi x can be exponential. Exponentially large. Yeah, but we should not have expected such a proof to work. We hardly use the fact that this phi is coming from a Turing machine which runs in polynomial time. We have to use that. This is true for any Turing machine. Nothing to do with the fact that the Turing machine has this nice NP property. The Turing machine is running in time, polynomial time. We're not using any of those properties. You want to use these. In particular, we are not using the fact. So haven't used the fact that Cx is computable. Firstly, we haven't even used the fact it's computable by a machine. It could be any function for all that you know over here. Cx. And by, it's not just computable, but it's computable by a polynomial time Turing machine. We have not used either of these facts. And in the proof, we are going to use both these facts. We'll need to. Okay. Sure. So how are we going to use this? We are going to use a couple of properties. Now I'm going to use the fact that M is a Turing machine. The previous description did not even use M as a Turing machine. It could have been any function. M of xu could have been any function, not necessarily a Turing machine. Now we'll use the fact it's a Turing machine. So once it's a Turing machine, we can make some assumptions. And I'm going to make a couple of assumptions to make our life a little easier. We first assume that M has 2 tapes. And this we saw, we can assume that M has 2 tapes. I'm going to make one more assumption, M is oblivious. So if there is a Turing machine, there is also a 2-tape Turing machine which is oblivious. And this one comes at most Q of n will get increased to order Q of n log n. That's what we saw. In class, we gave a proof which goes from Q of n to Q of n square. But let's assume you can do this with this extra cost. So if there was original one polynomial, this other polynomial that we'll be working with the extra assumption takes a little more time, but it's at most a logarithmic overhead. If you believe the theorem I gave in class, or if you stated in class without proof, or if you saw the proof in class, it was a quadratic overhead. So it's going from one polynomial to another polynomial. So that's one thing we'll use about M. So M is actually CFX is computed by a Turing machine, and the Turing machine we're going to have, we'll assume that it has these properties. It's an oblivious 2-tape Turing machine. And another property which here we are going to use a mix of both. So we want to say that I want to capture the satisfiability of psi x. So psi x captures that it is a satisfiable assignment. You want to somehow express this as a CNF formula. So let's look at what is the thing about a CNF formula. CNF formula, what is it? It's a conjunction of clauses. So it's sort of like a big AND of a constraints. There's a huge AND. The question is, somehow we can capture computation also as this big AND. So what does computation mean? Computation means, what is a Turing machine computation? It says, I start with an initial state, then I do step by step, I do some computation and come to a final step. If every single step is done correctly, then the whole computation is correct. You need to check that it's a computation. So what we'll try to do is, this AND will actually be checking, in some sense, step I is obtained correctly from step I minus 1. So we'll show that step I can be obtained correctly from step I minus 1. Of course, you have to do it step that the step 1 is initialized properly. And the final step is accepting. So those are. So computation basically means this. You have to start correctly, you have to do every step should be done correctly, and the final step should be correct. This one. Now, okay, we haven't changed anything. The point is, each step, what does each step depend on? Each step depends on what the head is seeing only at that local view of the head. So to say step I is obtained from step I minus 1, if we say if that involves only a constant number of variables, this particular thing can be written as a function which depends only on a constant number of variables, and potentially I can write it as a CNF formula. Why was this blow up a bad blow up? This blow up, pointed out this blow up from C of x to P of x, because this P of mod x is not a constant, and we can't afford super constants over here because that will blow things up exponentially. It so happened that if each of these steps involved only a constant number of variables, then each of these I could write as functions and then write the corresponding CNF formula for them and just take an AND of them. So I don't mind if this AND is a long AND. But as long as each step, it depends only on a constant number of variables, you can resort to whatever we did in the past. And we'll actually see how we can implement it. I've been quite vague here, but that's the main motivation. That is, a Turing machine is the fact that something is computable. It means that several steps have been carried out correctly, and each step requires only a very local view. What does one step require on? It requires to find out whether a step is being computed correctly. You just need to know what was in the previous head position, where the head was there in the previous position, and did you apply the transition function correctly? This is all that we need to know. So we're going to sort of state that, capture this fact that step I is obtained correctly from step I minus 1 involves very few variables. It doesn't involve the whole tape or something. It looks at a very small part of the tape, and hence I can write that as some function which depends on a constant number of variables, and then I can resort to this, writing this function as this one. So now, even though there's an L over here, it blows up by this L, because the function involves only a constant, this blow up will not cost us. And there will be several such. We'll have to do this for every step. So it will be a conjunction of several such CNF formula, but the number of such CNF formula is exactly the time of the machine. Therefore, it will still remain polytime. So you'll be seeing we are using both the fact, one, that it is actually this function is computed by a Turing machine. That's why we are able to write this. And the other is polynomial time comes from the fact that this number of ANDs here is at most a polynomial number of ANDs. So both the features which we sort of did not ignored in the previous thing will be used in the way we do this. Questions? Okay. So for this, I'll define a notion of what I'm going to call a snapshot. So a snapshot is, in some sense, the view of the head of the Turing machine. A snapshot is not the entire description of the Turing machine at a particular point of time. It's the view of the head at a particular instant of time. The snapshot will be, so the snapshot is going to be a member of, so what does the view of the head have? The head knows which state it is in. So it is some Q. And there are two tapes. It sees what are the contents of either tape. That's all is the view of the head. The head knows which state it is in and the two contents of the two tapes. Just the two symbols, not the entire tape, just those two symbols. So a snapshot is just an element. So snapshot Z looks like some Q, A, B. This means the head is in state Q and tape 1 has alphabet A under the head.
Letter A.
Letter A. as letter A, under head, and tape 2 as letter B under the head. And what's the Turing, this one? The Turing machine, you want to say you have a sequence of Z1, Z2. The computation of Turing machine goes like this, Z2, all the way up to Z, Q of mod X. We had to check that each snapshot is got correctly from the previous snapshots. Okay. So let's now say, so ZI. ZI is a function. So I want to say one particular snapshot. What does it depend? Does it, how many, what is the previous snapshot it depends on? So certainly, so look, if you look at, let's go back to this picture of the Turing machine. There are two heads. The snapshot is this one and the tape state here. So that's one thing. And the next step, it could possibly move this. It could move right on this and left on this. That's say time step T, and that is, sorry, that's, so the blue one is time step T, and sort of the purple or the violet one is time step T plus 1. So let's call it ZT. So ZT certainly is a function of ZT minus 1. What else is it?
Delta and AB.
Yeah, let's assume that delta is all constants. Delta, I'm going to forget about the description of the Turing machine. That's one fixed thing. Does it just depend on ZT minus 1, or is there a different snapshot also it differs on? ZT minus 1 is this snapshot. You need to know. So I'm going to talk about Z prev. So ZT minus 1 is, so I need to know what the snapshot purple is. For that, I need to know the snapshot blue certainly, because I need to know where the head, to know what the new state of the thing is, I need to know the state in the previous time step. So the head, so for example, so let me just say, so ZT itself is QT, AT, PT. ZT plus 1 is QT plus 1, AT plus 1, BT plus 1. So to know QT plus 1, you need QT, AT, BT. This delta will tell you this. So you possibly need ZT. Sorry, this is, I should have put all mixing up.
What is Z previous T and Z? Oh, okay.
Yeah, so Z prev T is the so now I'm going to make this one. It's an oblivious Turing machine. It's an oblivious Turing machine. Therefore, the position of the head at time T is not a function of the input. It's a function only of the length of the input. Okay.
What is Z?
Yeah, I'm going to define what Z prev T is. Wait a second. So let's define, let me make this. Let's call it Z prev 1T, Z prev 2T. So what do I mean by this? So notice that we made an assumption that the Turing machine is oblivious. So prev 1T is the previous time step, previous time at which, should I kept all of these as, this is T minus 1, and all of these, this is T minus 1, T minus 1, T minus 1, T minus 1, and there are more T's. So once again, to know QT minus 1, AT minus 1, BT minus 1 is sufficient. You can find out what QT is. There's a transition function tells you. To know what AT is, notice that ZT minus 1 does not have the information what AT is. AT is what was there on the tape previously. AT you don't know. But now you use the fact that it's oblivious. So let's, prev 1T is the previous time at which Turing machine was on tape on tape 2, on tape, so let's call it I, on tape I at the same position as time t. So this is the previous time at which you were at the same place. Okay. Is the definition clear? So it's the previous time. There could be no previous time. Then otherwise or bot. Because this is the first time you encountered this particular position on the tape. Then there was no previous time that you encountered this. This is for tape I. Similarly, you have one for tape 1. You have one for tape 2. This is what AT minus 1 and BT minus. So this is what AT and BT will have. AT needs Z prev 1t. BT needs Z prev 2t. Is that okay? I claim that once you know these two, then ZT is just a constant size function of these 3 snapshots. If you know these 3 snapshots, one is the previous snapshot, and the previous 2 and the other 2 snapshots when the head was in the same position as the violet thing, and head 1 and head 2, then just knowing these 3 snapshots, you know what is the new snapshot you're going to have. Okay. I see a lot of confused faces. So ask me questions. It's fine if you don't finish the proof of this. Ask me questions.
So one thing maybe is clear is like if prev, I mean like if the one of the new positions that you discovered, like this AT comma BT, these were locations you had visited earlier, then it's clear what they should be.
Yeah.
But suppose you had not visited it at all.
Then AT should be the blank symbol, because it's the first time you did. It's a blank. So
it depends on whether it's yeah.
So it's a.
It may be something else, right? It may be some symbol which is not reached at all, right? Like you have AT and BT at time, and all you need for ZT plus 1 is AT, BT, and the ones on the left and the ones on the right? For ZT plus 1.
For ZT, let's say ZT minus 1 to ZT. Yeah.
Suppose you are given ZT minus 1, you are given AT minus 1 and BT minus 1.
Yes.
And the head is pointing to these 2 guys.
Yes.
When a delta function is applied, you get ZT.
Yeah.
So you'll have these AT and BT, they'll be flipped. And all you need is guys on the left and right of AT minus 1 and BT minus 1, right?
Okay. Yeah.
Specify ZT. So you'll need like 3 guys on the 3 guys AT. You'll need AT minus 1, BT minus 1, and the guys on the left and right.
No, but you have to keep updating them. So you need the guy, but the point is for the next time step. I follow what you're stating, but you need to update them. Actually, so let me to Ram Prasad's question. Let me just let me just call Z prev 1t, which is on tape 2. And this one, let's not call it Z prev 2t. Let's call it just the input position. Input position. The input tape once again is a read-only tape, which has just notice the input tape has 2 things. It has X and U. Non-deterministic Turing machine. So let's go again. What's a snapshot? A snapshot is what the head sees at time t. ZT is a snapshot. It's the content of the head, is the state of the head and the position, and what is written on the 2 symbols on the tape in the input tape and the input tape and the work tape. Those 2 symbols. It could be long. If there are K tapes, it could be longer, but let's work with just 2 tapes. That's what particular snapshot refers to. And I want to say, if I want to know what ZT plus 1 is, what I need to know is the previous time snapshot of the previous time step, and what was there in these 2 positions in the input tape and the work tape the last time the head was over here. So last time the head was over here for this one. For the input tape, there is no last time. The input tape is never changed. The input tape has in the first. So in the input tape, what does it have? In the first n location, it has the input X. In the next n locations, it has the input q mod x. This is the input for the Turing machine. mxu is the input for x comma u is the input for the Turing machine. Therefore, the input tape has just this.
So for zprev, when you write zt, it needs to be zprev t minus 2t, or
no, zprev t. Just the previous step. What was there?
You have defined previous it.
So no. So there is. It's only tape 2. It's only tape 2. Prev t is only about tape 2, and the first tape is the input position. I think I've lost people over here. Let's go over this once more, and we'll do the whole thing a little bit again in the beginning of next lecture. Once again, what's a snapshot? A snapshot is what the head sees at time step t. It's not the whole tape. It's not what you see as an outside observer. It's just what the head sees. It's the state of the head and the 2 symbols it reads. And this 3 tuple is going to keep changing as you progress in time. It starts with some z1. So notice z1 will start off as, this will be, what will this be? This will be q start. This will be the start symbol. This is what z1 is going to be. And it's going to keep chugging along as it progresses all the way. And what we want to write is that what's the function of zt in terms of, okay, to know zt, what all do you need to know in order to write zt? And to zt, I want to say the thing that you need to know about zt is you need to know zt minus 1. That tells you what the state is. Then you also need to know what was in the head. So you need to know that at zt, you are asking at zt, this time step t, you want to know where the tape is on the input place. This is the input position. This is input position. Input pass t is the position on the input tape. Input tape at time t. So this will tell you. So in fact, what you need is y comma this one. So y, let's say y is the joint input xou is the input for the Turing machine. Input for Turing machine. For Turing machine m. So y is this combined input, and what you need to know is y at input position I. If you know this, you know exactly what is the symbol over there. And you also need to know what was the previous symbol at when the tape was at time step t. The head was previously at this. This will tell, the first thing will tell you, this thing will tell you what was over here. And I need to know what was over here. And this is captured by this. Questions?
So, I mean, maybe just to rephrase a little bit or something. So the point is, I mean, like if your current snapshot is looking at 2 letters on the 2 tapes and you're in a certain state queue, then you know what you did after that. So the Turing machine would have possibly changed those 2 letters in those locations and then change the state internally to some other, whatever, qt or something. But now the heads may have moved to some new locations. Now, the new locations could be of the following type. Either there could be a location that you have never visited so far, or it could be a location that you had visited sometime earlier in the past. If you had visited sometime earlier in the past, then you know what those locations are anyway because of some zprev t. So if it were one of those situations, then you will know this. But suppose it was a location that you have never visited, then one of the following happens. Either you are now encountering a blank symbol, or you are still encountering some part of your input. I mean, you just moved a little bit to the right in your input or something. So that is going to be captured by this input pause of I. So that's basically what we are saying. So we need to somehow populate what is the new locations your head is currently seeing. Either this is a location you've already seen, or it's a fresh location. But if it's a fresh location, it's very predictable. So either you move past your input, in which case you're going to be in a blank position, or you are still within your input, in which case you're just going to be reading the next bit of your input or the next letter of your input. That's, yeah.
So actually, we're out of time. So what is going to happen is the following. So for the key thing to notice, let's see what's going to happen. So prev of t and input position of t, I claim, don't depend on the input x because the machine is oblivious. So the main observation over here is the functions prev of t and input pos position at t are functions only of mod x and not x itself. In fact, they're not, because the machine is oblivious, because M is oblivious. For instance, one way of doing it is just ignore the input, take the all zero string with this particular input, just run it over the whole input, run it for the entire time. You can calculate at every time step where the input position was at this particular time, what the previous things are. You can find out this function. You can find out these functions by can compute these functions by just running M on input, say 0 mod x. That is, you ignore the input, take only the input length and run it on this, and you will be able to find out these. So once you have these, now I want to claim, now you can implement all of these 3 steps. Step I is obtained correctly from step T. You'll see that all you have to do is you have to check that this function which I have written over here can be uses only constant number of variables, which it does. It uses only zt minus 1, z prev t. So it's 3 variables here, 3 variables. So it's actually only 10. It's a function of only 10 variables over here. So this can be implemented. We'll say that this can also be done. This can also be done. So it'll be just a big conjunction of all of these. We'll see this next time. Refer it down. I'll recall the definition of snapshots and stuff, the beginning of the previous lecture, and complete the proof of Cook-Levin. This class took much longer, and sorry if I confused you guys. We will revisit this in the beginning of next lecture.
So would it help if we thought of this from the NFA perspective and the state space in the NFA?
Yeah.
Okay, sir. So we'll.
No, what was your question?
My question was, would it help imagining this thing not only from the perspective of just a Turing machine, but also from the other representation that is like an NFA and the state spaces in the NFA?
You're meaning in the non-deterministic world?
Yes, sir.
No, so not.
Or a DFA for that example. I mean,
where does DFA and NFA come? There's no.
So nothing, sir. I'm just wondering if I can think of the head and the letters from that perspective.
You can think of it, but DFA and NFA are easier to work with because DFA and NFA never change what is written under the head.
Yes, sir.
Finite automata. Turing machine is more powerful. So if you did not change it, this thing will become much simpler. The point is a Turing machine can overwrite things. Okay. And it can move left and right. So things become a little more complicated because of that. If, for example, in an NFA, DFA, you don't even for a DFA, you don't need to know a time step I, you're reading the ith bit.
Yes, sir.
This one. That's what it is. There is no question. It's not going back and forth. So here it's going to be a little more complicated. This prev and all are trivial over there because it only reads this. It never comes back to this.
Exactly. That's why I asked.
In a Turing machine, it's going to go back and forth. And you need this prev and this one to understand this. I will re-explain this at the beginning of next lecture.